A net ionic equation is a chemical equation that only shows the elements, compounds, and ions that are directly involved in the chemical reaction. Spectator ions are ions that do not take part in the chemical reaction, and they are found in the solution before and after the reaction. So let's look at an example of a net ionic equation. We start off with HCl as an aqueous plus LiOH, which is also aqueous, yields water as a liquid plus LiCl, aqueous. Now, if we're to write this out as a complete ionic equation, this is where we separate the elements and we make them all individual ionic compounds, if that makes sense. So, for example, hydrogen will have a +1 charge because that's just the charge that it holds. In addition, chlorine will have a -1 charge because if you find it on the periodic table, it is in column 17, which has a -1 charge. Then you go on to lithium, which has a +1 charge, and OH actually stays together as a compound. And this one, when you look at it, oxygen has a -2 charge, hydrogen has a +1, therefore it has a -1 charge. And that, by the way, these are all aqueous. And that's going to yield H2O as a liquid. We don't need to mess with H2O because it's a liquid, or in other cases, if there's anything else besides an aqueous solution, such as a liquid or a solid, you just don't need to mess with it. And we're going to get H2O H2O plus Li, which is positive, plus Cl, which is negative. And those two are also aqueous. So now that we have all these ionic, after we've separated these into individual ionic compounds, what we can do now is we can write the net ionic equation. And this is where we take the spectator ions that I talked about earlier, which are the ions that do not take part in the chemical reaction and are found in the solution before and after the reaction, and we can just get rid of them because they do not affect anything. So if we do that, we're left with just we're left with the hydrogen, which is an aqueous, plus OH negative, which is an aqueous, yields water. We're able to take out lithium and chlorine. We're able to do so because they're the same on both sides of the equation, and therefore we can just get rid of them. And we like doing this because this is an easier way of just looking at what really goes in the reaction, and like instead of having it feels like it's clustered with everything in there, versus we just want to know what is affecting what, and if it's not affecting everything, just get rid of it because it doesn't matter. So in addition, H2O is neutral. That's why it doesn't have a charge because hydrogen, 2 hydrogen makes a +2 charge, and oxygen is a -2 charge, making it 0. And now if we look, I can give a visual representation of this as well. So on the left side right here, we have, let me get a pencil. We have hydrochloric acid. On the right side, we're going to have, I believe that's lithium hydroxide. I might be wrong on that, LiOH. And then that's going to yield H2O, so water, plus lithium chloride. And you can see right now, right here, it might be a little difficult to tell the colors, but we have the different hydrogen and the different chlorine atoms. In this section right here, we have the different lithium and the different OH atoms. So the lithium are the purple, the lithium are the red, so that'll be that one, and that one. And so that's what we have on that side of the equation. And that's going to yield water, which we have right here, H2O. We have 4 molecules, and the molecule count isn't exact. It doesn't matter right now in these particle diagrams. The point is just to get the main point is just you can understand this visually. And that's going to be with the lithium and the chloride. Now, this would be the complete equation with HCl, LiOH, H2O, and LiCl. What we can do about this actually is we can subtract everything and we could rewrite it as if it was just a net ionic equation, which would make it a lot simpler. If we were to do so, we could actually totally get rid of this one right here. So if we just cross this one out, and in addition, we can see right here in our net ionic equation, we just have hydrogen over here and we just have OH. So we could actually rewrite this and we could just get rid of the chlorine and the lithium by subtracting those individual molecules. And if we were to do that, you could understand how less clustered these the reaction would look, because you'd have so much less on this side of the whole equation and so much less on this side, which makes it a lot simpler to look at. Now let's look at another example. So in this example, we have magnesium and sulfur. So magnesium, sulfur in an aqueous state, plus copper and chlorine in an aqueous state yields copper sulfide. Actually, I don't know if that's how you say it, but copper and sulfur in an in a solid. And then you have magnesium and chlorine in an aqueous state right there. So if we're to rewrite this as a complete ionic equation, you can see it looks very, very clustered. But we'll start off. So magnesium has a +2 charge. So that's why when we separate it, we put a 2+ up there. If we look at sulfur, sulfur has to have a 2- charge, which does make sense because it has to neutralize a compound. So its charge is 0. So that these two right there, just let me move that up. Okay, these two right there only are for that compound. So if we look at copper and chlorine, we have copper has to have a 2+ charge because chlorine itself has a -1 charge, but there are 2 chlorine, which means there's a -2 charge on chlorine, which means copper has to have a 2+ charge. Now, if we look at the rest of the equation, remember, we do not mess with anything else other than aqueous solutions. So as the CuS, right, that's the solid, so we're not going to mess with that. But we also have to look at the other side right here, which happens to be aqueous. If we do so, we can see that magnesium will have a +2 charge, just like before. In addition to this, the chlorine, because there's 2 of them, it'll just have a minus. So essentially, it's just saying there's a 2- charge. Now, this, once again, is looking very, very clustered. So the beauty about using ionic equations is we can transform all of this into just 3 different things. We're right here. So when we subtract on the left and right side, you see we can get rid of magnesium right there because they're same charge. We can get rid of copper. No, sorry, we can't get rid of copper. Magnesium is the only one that we can. Oh, and chlorine. 1 second. No, I take that back. I'm just looking. I'm getting confused between the video and the notes. Okay, so sorry. Okay, I'm back here. And we can also get rid of the chlorine right here. So because it's 2Cl, and they're both negative on both sides, we can get rid of those, which makes this so much simpler. Now, instead of having all this, we only have copper with the 2+ charge as an aqueous solution, plus sulfur with the 2- charge in an aqueous solution yields copper sulfide, or CuS, as a solid. And this, once again, it looks so much better this way. It's a lot easier to look at reactions if we're to do another visual reaction like we did with the first one right here, just to visualize it and to help us out with our chemistry. Now, let's take a look at one more example. This one by far is the toughest example. So we'll go through of the reactants and the products and everything. So on the left side, we have NaOH together as an aqueous state. Then we have HC2H3O2 aqueous, and this is a very weak acid, and I'll get into that in just a sec. Yields H2O in a liquid, so water, plus NaC2H3O2 in an aqueous. So that would be the balanced equation that we would look at. And then if we want to look at complete ionic, we would simply just, not divide, but take, essentially we're just picking it apart and then we're looking at the different ions and such. So just like that, sodium will have a +1 charge, which makes sense if it's just plus. OH, as we already know, as I discussed earlier, only has a negative charge. And then we get HC2H3O2 as an aqueous, and this actually has a charge of 0 because it is a weak acid. It doesn't, yes, because it's a weak acid. Now, if we look at the right side of the equation, you can see we have H2O as a liquid. This will also be neutral, but it's just water right there. Remember, we're not affecting that. And then we also have sodium over here, which is positive. If we pick apart this up here, and then we also have the C2H3O2, and we have a negative charge when we look at it because it no longer has the hydrogen. Now, if we were to look at this, and this, once again, looks super clustered, there's a whole bunch of stuff to look at if we're trying to make a reaction out of this or if we're trying to draw this out in a particle diagram. What the beauty about this is we can actually rewrite this in the ionic equation, and we can subtract a whole bunch of stuff. So starting with the sodium, we can get rid of the sodium on both sides because it's the exact same. And actually spoke too soon, but essentially, I know the sodium isn't even that much, but even by doing so, it makes it look less clustered. And then essentially, that's just because it's a spectator ion. So then we're just left with OH minus, and the charges stay the same, they don't change, plus the weak acid right here. yields water right here, and then the C2H3O2 with the negative charge as an aqueous solution. So yeah, there you go. That's how you do net ionic equations.